Hey everybody, I hope you're all doing well. This video I'm just going to go over some of the questions that some of you had on the Unit 6 multiple choice set. So I had a little technical difficulty, so I already did this one, and it was a great video, but I'm not going to redo it. I'm just going to talk through it this time. So anyway, in this one we have a spring hanging here and its length L0. Now we have to recognize this spring can stretch and it can compress. When we hang a mass on it, it will stretch a distance L1 and just hang there. And then we pull it down an additional L2 and release it. So it's going to oscillate up and down. This right here is the equilibrium position. All right. So we pull it down a distance L2, simple harmonic motion. It will oscillate now with an amplitude of L2. Now we don't know how big L2 is compared to L1. The picture, it looks like it's a little bit bigger. It may not be, who knows, but it turns out it doesn't matter. If L2 is a little bit bigger, it's going to go beyond this point, and it will then, remember, this is the point where it's not stretched or compressed, so it will compress it by that amount. Now if L2 is smaller than L1, it's going to come up here and stop right here before it returns, so it's stretched by this amount. Either way, the amount it's stretched if L2 is shorter or the amount it's compressed if L2 is longer, it's the same, and it's just going to be the difference between L2 and L1. So to get energy, these kind of questions, the College Board frustrates me, is I always feel like they're trying to catch you on this. So they talk about potential energy, but they do not say Earth is in the system. In fact, they say it's the mass spring system. So forget about MGH. Don't even think about using it because that doesn't apply here. So all we're looking at is the spring potential energy. So at the lowest position, we're going to have 1/2 kx squared. So again, if this is the unstretched position, it's stretching a distance L1 plus L2. So that's what I have there for the 1/2 kx squared. At the maximum height, it's at one of these two locations, either here or here. Either way, we're going to have 1/2 kx squared, where it's either stretched a tiny amount or compressed a tiny amount, and that amount is L2 minus L1. So this is our energy at the maximum height. This is our energy at the lowest height. So we just want the difference between these two. So you FOIL them out. That's what I have, these two. And then I'm going to subtract them, just final minus initial. So I wrote it out like that. We have to distribute the minus because we're going final minus initial. So anyway, you end up with that quantity, 2 times K times L1 times L2. In fact, we'll get a negative here, but it's asking for the magnitude, so we don't care about the negative there. Did it say magnitude? Yeah, it does say magnitude. That's odd. It's not a vector, so that wording's a little funny. But anyway, C is our answer there. Okay. And the next question was on number 3. So this gives a mass on a spring oscillating. Is it horizontal? Yeah, they're on a table. Okay, so it's oscillating. We have mass and period, and we're looking for spring constant. So right away, I'm thinking that equation because that relates all those quantities. Now, there's a way I would do this, but I'm going to check their answers just because I might be going down a path that they're not taking. I'll talk about that in a second. But anyway, option A, create a graph with the period of oscillation on the vertical axis and the mass on the horizontal axis. I don't want that because from this equation I can see period is proportional to the square root of mass. So if we plot period versus mass, that's not going to help us. B, graph period on the vertical axis and the square root of mass on the horizontal. That sounds like something that might work. So period and square root of mass. Okay, so we'll have some line here where the slope is going to be period over square root of mass. So anyway, use the slope to determine the spring constant. Okay, so if we just rearrange this equation, and we've got we can see y equals mx plus b. Anyway, our slope is the 2 pi over square root of the spring constant. So if we have that slope, we can just plug that in and get the spring constant there. So that's looking like our answer. We eliminated A. C, period versus the square of the mass. No, again, period is proportional to the square root of the mass, so we don't want that. And D isn't going to work for us either. Okay. Now, if I were doing this on my own, I probably would have plotted period squared versus mass. That's how we've done it in class. It all works the same. So anyway, that's that. Okay, the next one is number 4 here. We've got a mass on a horizontal spring. It's going to oscillate back and forth. We're getting all the information. Anyway, the students want to have an experiment where they know what the force is at A over 2, where A is the amplitude. All right, so this one, this frustrated me a little bit because I didn't really like their answers. And I had to look at their explanation, and it's pretty vague. But anyway, C is our right answer here. Determine the magnitude of the slope of the best fit line of period squared as a function of mass. Okay, so again, 2 pi square m over k. Whenever I have a spring oscillating, I'm going to think this equation. It's really one of our few options with that situation. So period squared versus mass. So period squared will equal 4 pi squared over k times mass. Okay, so I just squared both sides there. All right, so period squared versus mass, so the slope is this quantity 4 pi squared over k. Now, the thing that frustrates me is they're saying get the slope of that, multiply the result by a over 2. So that, to me, is implying I'm going to multiply this value by a over 2. That's not going to get us the force because even the units don't even work out. Now, we can use this, so I'd rather they say use the slope to, or use the slope with a over 2 to get the force. I don't know, something like that. But anyway, we cannot just multiply this by a over 2 to get the force. Anyway, our next step, because it's on a spring, F equals kx. Okay, so somehow we're going to use this. We're actually going to take 1 over slope times 4 pi squared and then multiply that. So that really is the spring constant. And then multiply that by the distance it's stretched, which is a over 2. So that'll get it. I guess reading the other options, none of the other options make remotely any sense. So C is our best option in that case. And the last one is number 8. This is a classic example of them just giving you too much information, or they're just trying to confuse you with the information they're given. So we give this velocity time graph. So my mind goes, oh, velocity, how am I going to use that in this? Velocity spring, oh geez, what is that? But you don't need the velocity actually, okay? The x-axis, time, that's what's going to help. So one complete cycle is to this point, that is 3 seconds. And we have a mass here, and we're looking for the constant. So our period equation, 2 pi squared of m over k. So the period is 3 seconds. 2 pi square root mass we're given is 0.6. And then solve that for k, and I bet you get that 2.6 newtons per meter. Okay, that's it. Thanks for the questions. I appreciate helping you out. So let me know if you have any other questions.